Okay, thanks everyone for joining. I'm not sure if I come through well. I have poor connection here, but probably Kent doesn't need many words to introduce. He have been in field for many years and made a big contribution, mostly compiling data from geochemical data and geochronological data that widely used by community. And most recent of his contribution was on combining uranium, lead, and lutetium hafnium data, which led to new interpretations on plate tectonics, and I guess part of it he will be presenting here. So I'll pass it to Ken.
Oh, okay. Great. Thank you, Andre. I'm fortunate to be here with you this morning. When I got up today, the electricity was off in this part of New Mexico, and it wasn't clear when it was going to be back on again. It wasn't too long ago that it did come back on again. Anyway, what I'd like to do is look at some of the various aspects of the Mesoproterozoic, some of those that have been characterized as unique to this period of time, and some of those that may not be unique to this period of time. First of all, the boring billion, this term, the first time I ran across it was when Dick Holland started using it back in the early 1990s. And he came up with this term based on two carbon isotope anomalies, the Condie down here at about 2.1 GA, and then the Neoproterozoic. And there was no more carbon isotope anomalies in here, and so I called it the boring billion. But certainly in terms of tectonics and magmatism and other things, it's anything but boring. And of course, this is also bracketed by the growth of oxygen in the Earth's atmosphere, the GOE back here at about 2.3, and then the Neoproterozoic growth up here. Now, what I want to mention first is talk a little bit about A-type granites, because these have been used to characterize the Mesoproterozoic. This is a beautiful outcrop in the field of one with a large K feldspar megacrust. The first place that I really ran across these in abundance was not in the Mesoproterozoic, but it was in the Archean in Zimbabwe. This is a picture on a field trip I was at in 1989. We're standing on an A-type granite, 2-point GA, and these granites are very extensive in Zimbabwe. Ebbe was one of the first to attach a geochemical definition to A-type granites, and he divided them into two groups, A1 and A2, based on niobium, yttrium, cerium here, and also some major elements. The A1 group, these are largely hotspot related granitic rocks, and they occur in oceanic areas, on continents, every place virtually, in stable regimes. I'm not going to talk about those very much on the continents. They're mainly pegmatites and carbonatite related things. But it's the A2 group down here that I'm going to focus on. These are the granites that are characteristic of orogens, the late stage of orogens, and for the most part, they're not found on cratons. There are some exceptions to that, but for the most part, they're not. Now, if you look at our database, which I had in 2010, which is about 450 samples, this is the frequency over here, and this is frequency of number of plutons. And it's been known for some time that there's a lot of A-type granites in the Mesoproterozoic. You see this big peak here at about 1500. This is our database today. We've come from 450 up to over 3,000. And again, we're dealing with the number of plutons here. The yellow stripe here is the Mesoproterozoic, and that will be so on most of the following diagrams. You can still see we have a large number of A-types here. These are A2 types in the Mesoproterozoic. But notice what's happened. The number of A-types granites has grown since this time, and especially it has grown in the last 200 million years or so. This peak here is still growing. This is largely in Eastern Asia. We have one here in the Neoproterozoic, and even those back here in the Archean are growing. One of the problems in looking at the frequency of A-type granites is how do you define frequency? If, for instance, this is a recent study of A-type, Devonian A-type granites in the Argentina. If you look at a map here, these two symbols here are both two different A-type granites of this age in Devonian. And if we look at a larger map, that is this area here is the detailed area up here, we see that they're part of a much larger complex of A-type granites. And there's at least two phases down here, maybe more. And then if we take this map and we go to a smaller scale map here by Cordoba, we see that this whole body is larger than it is, and that there are several other bodies here of the same, probably the same A-type categorization, even there and up here too. And so the fact that we put 2 plutons and count 2 in the frequency, there are many more here. There's just no geochemistry on these yet, so we're not sure they're A-type, but the chances are that they're A-type, and they're much more frequent than the map would suggest. And this also comes out of recent studies by Li et al. In the central China, or the North China origin here. The orange color, the yellow color are largely A-type granites. You can see a large batholith-sized body up here made of different plutons. These are all around 200 million years in age, but if you look carefully here, you can see many other plutons of this age, and some of them very small, and they go all the way across clear over to here. And so if you're doing a pluton count on A-type granites, and these all happen to be A-type with this color, you've got a vast number of A-type granites in this origin. So if we come back to the frequency of A-type granites here, those that I just show are chiefly over here in Eastern Asia, and they are growing in number. They're growing in number. It's long been known that this peak at 1450 or so was dominated by A-type granites in central and southwestern Laurentia. And many of these are in the basement. They're from drill core data, so you don't know which ones are really part of the same pluton and which ones aren't. And so it's very hard to come up with the number of plutons when you're dealing with these guys in the basement, unless you happen to have geophysical data that you can define the pluton size. If we look back over here at the Central Asian orogenic belt, the areas in orange here are belts which contain a lot of these A-type granites, and they're all accretionary orogens. As the various oceans closed in here, as starting as early as the Neoproterozoic, or maybe even earlier, and of course even going on today if you go down to the Australian plate. But certainly most of the action in here is between the Neoproterozoic and, say, the Cretaceous. And these belts have A-type granites that range in age over that complete range. So there may be a vast number of A-type granites that we're not counting in this area. If we go to the Mesoproterozoic now, this is a map I put together several years ago with Nuna reconstruction here with Laurentia, Baltica, Amazonia. Amazonia may not be here. We can't constrain the longitude very well on that. But the red dots here, A-type granites that are in this 1400 to 1500 MA group. Notice where they're at. For the most part, they're in what we call the Great Proterozoic Accretionary origin, which is divided here into two age groups, which extends from Laurentia to Baltica and perhaps to Amazonia. And they're in the origin. They're not in the Craton, with a few minor exceptions, like there's 3 here in Baltica and a few down here in Amazonia. Now, if we look at the little bit about how juvenile these A-type granites are, this comes from a study of John Goods and Jeff Vogt back in 2006 on an epsilon hafnium diagram. We can see here the chondritic uniform reservoir and the juvenile component up here, the depleted mantle component. And if you look, these guys fall in this area here. They're largely in the juvenile field. They have positive epsilon happening values. And the modeling of most of these guys in the US here suggests they're produced by either partial melting of the lower crust, and that lower crust can't be much older, 200 or 300, 400 million years older. When you look back here at the model ages, extrapolating these lines backwards. Or they may be actually a mantle origin. Certainly they have a strong mantle component. Same thing is true for all the new work that I've seen going on in the Central Asian orogenic belt. Look at epsilon hafnium again. The purple box and the light blue box here are both A-type granites. And relative to Chur down here, you can see that the larger proportion of them in both cases are in the positive epsilon field, indicating a strong juvenile component in these granites. So how can we rationalize A-type granites forming in these orogens? This is a model that we proposed back in 2013 as a possibility, where we have a convergent margin. This model is for the 1.5 to 1.4 A-type granites in the southwest and south central part of Laurentia, where we have an arc system on the south side. And we have these granites, which are in sort of a back arc position here. And for instance, these could be produced by partial melting of the lower crust, and that lower crust is not much older than the age of the granites, so it carries, again, a largely juvenile signature with it, with a mantle component adding to it here in this back arc position. And as time goes on, this arc system could advance forward with subduction erosion occurring here, removing this material as we go. And in that case, if this model is viable, the A-type granites should move inland. And we haven't really looked at this in detail yet, but this would be a good test for this model to see if, in fact, these A-type granites get younger as you go inland towards the craton. Something that's on my agenda for the future here. Now, something else I'd like to mention here is the anorthosite situation. Both Lou Ashwell and John Bedard have published extensively on this, that the anorthosites appear to be these massive type anorthosites and associated gabbros that characterize the A-type association. This is a photograph of one where you can see the strong layering in the massive anorthosite here in Norway. It's a billion-year-old example. The Archean, however, appears to be characterized by a different type of anorthosite. I've only seen one of these, but Lou Ashwell has described these in detail in some of his work. This is one of his photographs showing these large megacrystic plage crystals. And these, in contrast to the massive type anorthosites, which are large layered intrusions, these are generally much smaller. The ones I've seen are usually dikes and sills. If we look at the frequency of these bodies, and again, we're back to the problem of how do you count these bodies, but these are counted as individual intrusions on this. And they're divided into the massive types and the megacrystic types. You can see that indeed the massive types are abundant here, but they're not especially limited to the Mesoproterozoic. They go earlier in that. In fact, we have quite a few that are found here in the late Neoarchean, and they come on right up into the Phanerozoic. The megacrystic types are characteristic of the Archean. there could be significant biases, especially in this peak over here. As we've known for a long time, a large number of the bodies that form this peak around 1GA are found in one geographic region, and that's the Grenville area here in northeastern Canada. And this strongly biases this peak from this one geographic region. Something else I think that's interesting is that the exhumation level of granites, which are A-type granites, which are associated with A-type anorthosites, can be important. This is an example where rafts of anorthosite have been brought up in an A-type granite from an area in southern New Mexico. This is approximately a 1.4 billion year of granite studied by Ginger McLemore. But these little black blobs here, I used to take my igneous petrology class in here. These are beautiful little rafts of A-type or of massive type anorthosite. Some of them are very small, a few tens of meters in size, and they've been brought up in this A-type granite. And so if indeed we got a greater level of erosion here, we might get down to where we're seeing these bodies. These have also been reported in Phanerozoic A-type granites. So if we look at the possible effect of exhumation level on massive anorthosites and A-type granites, this is one of Mike Brown's diagrams where we have pressure on the vertical axis, temperature on the horizontal axis, and he shows in here various metamorphic suites of different PT conditions. If we first of all look at the Proterozoic examples, which is where most of our exposed A-type granites are, the exhumation level is generally in this range here, which is maybe 15 to 30 kilometers to expose those. But if we go to the Phanerozoic, most of the Phanerozoic examples are lesser exposure levels. They're perhaps from 15 to or 10 to 20 kilometers or so. And so if we were to actually erode deeper in the Phanerozoic ones, it's possible we could find these massive type anorthosites. And again, we see rafts occasionally of them in the A-type granites, indicating that they are at depth. And so that being the case, the younger examples up here show very few massive type anorthosites. This could be largely due to an erosion effect, that we haven't eroded deep enough to see these yet. I recall one in the Southern California batholith where we have a beautiful exposure of a massive anorthosite associated with this Mesozoic batholith, where the erosion level is deep enough there that it's cut down to expose that. Something else that has been used to characterize the Mesoproterozoic or passive margins, and Dwight Bradley in 2008 published his classic paper where he looked at the passive margins with time. And this is the graph showing from his data the number of passive margins, their start dates versus age. And he showed that during the Mesoproterozoic here, which is the time of the evolution of Nuna, both the formation and the breakup are shown here, and the formation of Archean, that there were very few passive margins that came into existence at this time, something that he felt was characteristic of this time. However, I've been working with Sergei Pizarevsky in the last few years, and he has been putting together new reconstructions for Nuna. We have a paper now that's just been submitted that has this new reconstruction on it. This is the picture that he comes up with at about 1500 AD, which is around the time of maximum packing of Nuna. And I have added to this accretionary orogens. And you can see the large accretionary orogen, the great Proterozoic orogen, which may go all the way from the Mawson plate up here, which is in Antarctica, around Laurentia and into Baltica. Now again, there's uncertainty in the position down here. This goes into India, which Sergei places here. Others place Amazonia over here. But in any case, you can see the distribution of the accretionary orogens around the edge of this supercontinent. Now, we're going to jump ahead to about 1200 now, where this supercontinent is broken up. 1200 is the time of approximately maximum dispersion. And now I have added here, in addition to the accretionary orogens, passive margins that are identified as these plates break up. For instance, up here, if you come to what will become Australia, these three plates, and Antarctica, we'd have a passive margin along this boundary, which broke off from over here, around at least two sides of Siberia. We have passive margin. We have one along the, what is today the northern edge of Laurentia here. It probably went further than that, along at least one side of the Congo and Tanzania area, the North China Craton, India, and the Kalahari Craton. So these are passive margins, the minimum number that had to come into existence between about 1450 and 1300 MA. So if we start here now with Bradley's distribution of passive margin start dates, and we revise this to add the ones that now come from the work of Pizarevsky et al. And our work here in paper, which is a paper that's been submitted, we see there are many more passive margins that exist in the Mesoproterozoic. And in fact, our data suggests there's a minimum of 12 passive margins that come in at this time. So the Mesoproterozoic may not be a time of no passive margins, but few passive margins. It's just that they've gone unidentified. Now, what I'd like to do now is skip over to some other things that are unusual about the Mesoproterozoic and have withstood the test of time. Let's go to the greenstones first. We've studied greenstones since the 1970s, and I've sort of kept track of their frequency with time. Greenstones are just successions that are dominantly mafic volcanics, but then they also have volcaniclastic rocks and a variety of other rock types, but they're dominantly mafic volcanics. This is my ongoing update of the count of these greenstones with time. And you'll notice that indeed, in the Mesoproterozoic, there are few greenstones. There are a few greenstones that have been recognized in this period of time. And if we go over to granitoids, this excludes A-types now. These are calc-alkaline granitoids, TTGs. And we look here, we see a similar situation. And I've tried to keep this up to date with time. But again, we've got the problem of how do you count granitoids. But if you look at the Mesoproterozoic here, again, you see a low. Now, we start to pick up granitoids towards the end of this, when Grenvillean time, because here we start getting the Grenvillean collisions, and we get collision of granitoids in here. But there's certainly a sparsity up here during most of the period of time of the Mesoproterozoic. Now, this is a graph that Nick and I are working on, Nick Roberts. This is one of his graphs that he's recently made. It shows some geochemical characteristics of granitoids with time. What he's plotted here is a secular change in yttrium plus niobium with time. Now, yttrium, first of all, A-type granites are very often enriched in high field strength elements and rare earth elements. And yttrium niobium is commonly used to characterize A-type granites. I think it's either 50 or 60 is the value that's taken of ppm as the dividing line with A-type granites. So over here is yttrium plus niobium, and here's your statistical fit of the data. You can see how much data we have by the gray dots in here. The blue areas here give a measure of, I think it's 2 sigma uncertainty in a 100 million year moving window. And if you look at this, during the Mesoproterozoic here, we definitely have a high in this ratio. And if that indeed reflects a greater proportion of A-type granites at this time, we have to ask ourselves, what does that mean? Now, that is not the only explanation, only possible explanation. Still far in the Phanerozoic types, we have a relatively few chemical analyses and of A-type granites. And so as we get more and more A-type granites over here, this line may move up. If it moves up, well then it'll be in the same range as the Mesoproterozoic. Another thing that appears to be missing in the Mesoproterozoic are mineral deposits of certain types, and this has been known for a long time. Here in the Mesoproterozoic, for instance, you look at orogenic type golds, which are the gray bars here. You see there are virtually none of them. And that's true also of volcanic massive sulfides and copper porphyries. They show a pattern much like this. And that's not too surprising, because the orogenic gold, the massive sulfides, and the copper porphyries are all associated with greenstones. And if greenstones are low in this particular period of time, it's not surprising that the mineral deposits associated with greenstones are going to be low in that period of time. This is work that I've been doing with Steve Pitts now for many years. We've been compiling zircon ages and a variety of other things with time and looking at these. And this is our most recent compilation, which has been submitted for publication, also for review for publication. The first two graphs up here are age counts of igneous and detrital zircons. And you'll notice, and this has been known for some time, that here's the Mesoproterozoic. It's outlined with the dashed purple lines, that these are times of relatively low numbers of ages. And it's not till we get towards the end of this in the Grenvillian times when we start picking up Grenvillian granitoids that we start to increase the number of zircons, both detrital zircons and igneous zircons. Incidentally, in our detrital database here now, we are approaching 1 million zircons in this database. Now, to look at the juvenility a little bit more detail, this is a graph of epsilon hafnium T with time, and it's expressed a little differently here. It's expressed as percent greater than 0. So this gives us an idea of those that are in the juvenile field. They have positive epsilon hafnium values. And if we look along here in the Mesoproterozoic, we see that the values are typically 50 to 75% juvenile or greater than 0. So again, there's a significant juvenile component in the Mesoproterozoic. Now it's interesting though, and I've added two other graphs that we've just recently put together. One is from lip ages. We have close to 900 lips in this database. And the other is from model rhenium osmium ages, rhenium depletion ages. And if you look at the lip ages, the lips don't seem to pay much attention at all in Mesoproterozoic. Each one of these episodes, they just go banging right through here. And the same thing appears to be true with the rhenium osmium model ages. We don't see much of a difference here. They seem to go right on through here. And so this is a very interesting relationship because it suggests that the upstairs, the continental lithosphere here somehow may be disconnected from what's going on in the deep mantle. Let's look at orogens for a while. This is a graph that Aki Johansson has put together as part of a big paper that he's preparing with many authors. And this is for the two provinces, the Spectral-Norwegian province in the Baltica area and the Grenville province in Laurentia. And these is based on the frequency of zircon ages in granitoids, which Steve Pitts have put together. The yellow band here represents, again, the Mesoproterozoic. And interestingly enough, as we've seen with time, that there is a minimum in orogenesis and associated magmatism during the Mesoproterozoic. But the beginning and the end of the Mesoproterozoic, we have major magmatic and orogenic events. The Gothian, Archean here, and the early second region here. Down here, the Labradorian and phases of the Grenville orogen. But we still see a minimum number in at least a period of time from the order of 1250 to what, 1450 or so. Mike Brown has shown the same thing when he looks at metamorphic mineral assemblages. This is temperature pressure gradients here with time, and the Mesoproterozoic is shown in blue here. If you look at the distribution of his high and intermediate gradient metamorphic rocks, there's a high population of them in here between about, what, 1700 and 2 GA. And again, over here around 1 GA, but not much in the Mesoproterozoic. And that's related to, we have the high frequency of orogens over here, both collisional and accretionary orogens, and also here, especially collisional orogens here, which are responsible for these metamorphic rocks for the most part. A recent study by Ming Tang has shown something else very interesting. Ming has looked at detrital zircons and the europium anomaly in detrital zircons and shown that this europium anomaly is related to the thickness of what he calls active crust. This is orogenic crust, largely in accretionary orogens. And this is a graph he has made of his estimated crustal thicknesses with time from the detrital zircon europium anomaly index. And you'll notice that in the Mesoproterozoic, which is the gray band here, that there's a minimum, distinct minimum in the thickness of the crust at that time. We have, for many years, looked at the distribution of continental crust provinces, and this is a map I put together several years ago with the juvenile continental crust provinces shown here. Of course, this is very difficult because you get reworking of crust, you get crust that's buried and inaccessible. So a map like this is never very quantitative, but I would like to call your attention to a low number here for rocks in the 1.6 to 0.7 GA. Only about 7% of the surface area of the continents seems to fall in that category. We can look at this in a different way here by looking at the percent by map area at the surface. And I've plotted this up two different ways here. One is by equal increments of age, 500 million year increments, and the other is by geologic eras in the Precambrian and Phanerozoic also. I have used both our data and Walter Mooney's data. Over here, I've used our data from 2012 and 2015, and Walter's data from 2018. And the interesting thing is here, no matter whose data you use, you get a minimum, you get a low here in this 1,000 to 1,500, indicating that for some reason there's a sparsity of crust of this age. Now, this is not all juvenile crust. This is also reworked crust that has a prominent age in this range. So it's juvenile plus reworked that falls in this age range. But however you do it, there's a minimum there for some reason. What is that reason? Well, Dave Scholl got me thinking about this a few years ago when he showed that a large amount of crust has probably been removed from the Andean origin over here by subduction erosion in the last 250 million years ago. 250 million years ago, he places the trench out here, and approximately 600 kilometers have been removed largely by subduction erosion, he's suggesting, in the last 600 million years. Now, how did that happen? Well, as the Atlantic opened over here, South America moved out over the Nazca Plate, and subduction erosion was enhanced along this boundary. Well, I got to thinking, well, could this also be the case when Nuna broke up? If Nuna broke up in a similar fashion and overrode the surrounding oceanic plates, could we start to lose material by subduction erosion in a similar manner? So if we come back to this 1500 million year paleogeographic reconstruction of Serges, we have this giant accretionary origin around a large portion of this continent. We have it around North China. We don't know whether it was around Siberia here yet or not. It could have been. It's not exposed there. It's certainly around the Kalahari Craton and around Amazonia. So as this supercontinent began to break up, is it possible that we lost material around these accretionary origins? So just looking at it back to this cartoon-like diagram I showed to begin with here, we have a bunch of things that seem to be unique here in the Mesoproterozoic. There seems to be missing crust. These crustal provinces are not as abundant as they should be. They're certainly missing zircon ages in this time, both detrital and igneous. The crust, on average, the active crust, continental crust, is anomalously thin. There are missing orogens in this time. And actually, the ratio of A-type to I-type granites increases during this time. I wonder if all of these could be related to the breakup of Nuna, largely by extroversion, of which Nuna overrides the oceanic plate, and we get enhanced subduction erosion and sediment subduction, both of which could add to explaining these features over here. So as that happened, we would start to get rid of crustal provinces here. We get rid of granitoids, we get rid of greenstone belts, we get rid of the zircons they contain. We could thin the crust on average. We're going to be eating away at orogens here. And maybe this ratio of A to I granites could go up because we're selectively taking I granites out. And what's happening to the A-type granites, well, shown by the black arrow, they're moving inland. As we eat away here, they move inland. And again, this would be an interesting test for this model to see if time goes on here in the Mesoproterozoic, if the A-type granites young towards the Archean cratons here in the center. So I'm just about ready to wrap up here. I'm leaving hopefully some time for discussion today. Could subduction erosion sediment subduction accompanying the breakup of Nuna account for the sparsity of Mesoproterozoic crustal provinces, orogens, greenstones, granitoids, mineral deposits, detrital zircons, and thinner crust? I'm throwing that out as a possible model to think about. Certainly, whatever mechanism we come up with, it's got to somehow explain all of these discrepancies or unusual features of the Mesoproterozoic. And if it was this mechanism, then we have to ask, why didn't this recycling of accretion layers occur during the breakup of later supercontinents? Why did it only occur during the breakup of Nuna? And then I would say, could it be due to the extensive overlap in the breakup and assembly phases? There's more introversion involved with the breakup of Rodinia and Pangea. And the accretionary origins were preserved. They weren't recycled to the same extent as they were during the breakup of Nuna. That's something that I think needs to be looked into in greater detail. So, conclusions. And my conclusions are short-lived conclusions usually. A-type granites, and these are the type 2, they're characteristic of convergent margins. They're widespread after the Archean with abundance peaks at 14 to 1500, at 600 to 700, and at 100 to 200. And they are accompanying the breakup of supercontinents. Massive type anorthosites occur from 2.7 to 1 GA, and they are found in accretionary orogens at exhumation depths greater than 15 kilometers. And there may be more of these than meets the eye. That's because our erosion levels are not great enough in the younger orogens to expose them yet. Minimum of 12 passive margins came into existence during the breakup of Nuna between 1450 and 1200 in May. Mesozoic crustal provinces, and this includes greenstones, I-type granites, mineral deposits, and orogens may have been preferentially recycled into the mantle during Nuna breakup. And finally, all this work to me suggests that there's really no convincing evidence to support a return to a stagnant lid tectonic regime on the Earth during the Mesoproterozoic. I think I'll stop there and see if people would like to bring up some of these points and discuss them.
Great, thanks, Kent. So now if anyone has questions, you can unmute yourself and ask question, or maybe type it in chat or raise hand or whatever.
Kent, this is Kevin Chamberlain, and as always, you present an incredible amount of data and make some great conclusions, or I should say some summaries. I have to disagree with your first two conclusions, however. As you pointed out, when the continental crust that the 1-4, in this case, but the A-type granites are intruding into, when that is not much older than the granite, you don't have much isotopic leverage to determine how much of the material came from the mantle and how much of it came from melting of the crust. And so that remains an enigma. In the case of the 1-4 granites in the Rocky Mountain region, there is a lobe at the far north, the Mule Creek lobe of the Sherman granite, that intrudes through Archean crust. And at that point, and for that granite, there is significant isotopic leverage. In the study that Carol Frost and Ron Frost did in 2001 and 2002, it demonstrated that there can be no more than 30% continental crust involved in the production of the Mule Creek lobe. So nearly over 60% of that is coming from the mantle. The second point is that the age progression of those granites is the opposite of what you're proposing. The oldest granites are in the north, the youngest granites are in the south. And the third point I'd make about that event is that people often forget the Belt Basin up in Idaho. But that's a significant mantle. It's a triple junction. We have two of the lobes preserved as the Belt Basin. It was a zone of extension from 1470 to 1380, the same period of time that these 1-4 granites are intruding into the more southern portions of Laurentia. And so I think while you've pointed out a lot of interesting characteristics of this period, the Mesoproterozoic, I think many of them can be explained by an alternative model where mantle processes are dominating the Earth at that time. And that's why we are seeing this difference in the proportion of A to I, for example, and the lack of crust and the lack of zircons. So all these observations you made are valid, but I think there's an alternative and quite opposing model that fits them as well. So I'll stop at that point.
Thanks, Kevin. I'm glad there is another model out there. And I agree with you that the isotopic data suggests that in some of these A-type granites, there's a strong mantle component. The hafnium isotope data, I suggest that when you consider them all, not just the ones from Wyoming, that there's a strong, in the modeling that's been done by various individuals, and many of these have a strong lower crustal signature also. So there could be both. I don't have any problem with having a strong mantle component in some of these.
Okay, Taras Jerry also asked question, are there any short-term analogous periods of the Mesoproterozoic and the Archean?
I'm sorry, I didn't understand the question, Andrew.
It's in a chat room, but
yeah, I can repeat it. Ken, what I'm curious is, can we detect anything, any period in Archean which is similar to Mesoproterozoic in terms of its petrological characteristics or whatever, you know, characteristic you listed in your set of indicative characteristics?
I don't know of one that has this, say, the sparsity of greenstone belts or the sparsity of granitoids in the Archean. I don't think it has been documented if there is one there.
And I have another short question. Can you think of very punctuated intermittent subduction as being an explanation for Mesoproterozoic, for example? Because there are some models that may predict that you have some sweet spot of this punctuated subduction in the Mesoproterozoic.
Yeah, I think it could be intermittent. In fact, I think the zircon ages, when you look at them in detail, they definitely show episodicity, okay? They definitely show episodicity, but so I think you definitely could have intermediate subduction going on there. I don't see why not.
Thank you.
So there is also a question from Jean Badard, and maybe my my connection is not good. So maybe Jean, you can sort of present
Sure.
your question yourself.
Just two bookkeeping questions really to help me understand what you're doing. How do you fit the Rapakidi granites into your story? Or do you see them as the A types or I types? And
A
how
types.
does that work?
Mostly A types, yes.
Okay. And how do you define a Phanerozoic greenstone? I mean, do you include flood basalts or only metabasalt units and orogens?
No, these are largely submarine greenstone successions. They don't include lips, they don't include flood basalts, they don't include continental rift basalts.
Okay, I'm confused. Give me an example of what you consider a Phanerozoic greenstone belt.
I'd have to look at my database. There are many of them in Japan and in California. The accreted terrains in California, many of those have Mesozoic greenstone belts in them.
Okay, I think I understand what you're doing now. Okay.
Okay. Was a question from Bodo Weber. How do you find out the ages of passive margins? Any datable material?
The ages of plate margins. Of course, that involves interpretation as well as good geochronology. You have to be able to correlate your geochronology with the rock associations which you think are plate margins. And that's not always easy to do.
Okay, and when was a comment from Nick Roberts, the record in Phenoscandia is near complete, no intermittent subduction in my opinion. I don't know if you have any response on it, Kent.
I don't, I'm not that familiar with Phanerozoic to respond to.
Okay, any other questions? So,
It's Richard here, or Paul, Richard, okay.
Yeah.
Let me ask you a quick question first. Thanks, Kent. That was a neat overview. You showed major passive margins along two sides of the Siberian Craton, and I wondered what you were referring to in those, what provided constraints at 1500. And the reason I'm asking is partly that we have been thinking that Siberia was attached to Laurentia, to northern Laurentia, you know, up till around the 720 shared lip events and broke up at that point. And also because there is a 1500 million year old lip event in Siberia, but it's on the northern side. And so I think the passive margins you were showing were on the southern side, but if there was a breakup associated with 1500 associated with Siberia, I would have put it on the north side. Anyway, I'm just curious what the constraints are for those two major passive margins.
If I can bring my share screen back up here, we can maybe find that picture again. Let's see if I can, yeah, here. Well, actually further back. This is Sergei Pizarevsky's reconstruction. And the conclusions I based on that are based on his reconstruction, which is based not on just paleomagnetism, but a variety of geological signals that can be correlated. Now, I assume that you do not like this position of Siberia right here. Is that what you're saying, Richard?
Yeah, well, yes, Sergei and I have certainly discussed this lots, and you know, on the basis of the lip matching record between Siberia and northern Laurentia, I'd have it closer. Sergei prefers a gap. I think there's some discussion around the paleomag. Dave Evans may jump in or not about the paleomag comparisons, and but Sergei definitely prefers an open fit there. But I was more specifically asking about the two passive margins that you drew along the Aldan shield on that side and also on the southern side in this view. And I'm not aware of the units that would be linked to that. There's some units down in this southern, the near Lake Baikal area that I think it's the Barusa sequence that were thought to be older, but I know we have some sills dated at 1600 suggesting that they are older sediments there. So I'm just wondering what the specific sedimentary groups you have there that were suggesting a major passive margins on both things at that time.
I'm not familiar with those, Richard, to answer that question, but it seems that even if the Siberian shield is not located exactly like this, if it's turned around or twisted one way or the other a little bit here, as it moves out, when we looked at the 1200 picture, the Siberian shield is way out here someplace.
Well, I think there's some debate on that because we certainly think that we have a shared large igneous province at 720. We have the Franklin event in northern Laurentia, and then we have the Irkutsk event in southern Siberia. So we actually have been thinking on the basis of matching lip record at a number of times, and also at Mackenzie Dike swarm time, a potential match in southern Siberia. So I'm not convinced of Siberia having moved away until at 720.
Okay.
So,
yeah, that's very interesting, and certainly that would be a powerful constraint against having it move out there. That's something that perhaps you and Sergei ought to discuss, because I am using his data entirely.
and we've discussed. Yeah. Okay. No. Okay. Thanks. Yeah. But I'm not sure. There's not that particular line you drew was not necessarily based on then the some specific sedimentary sequences. It was
it was not based on the sedimentary successions at all.
Yeah, it was just based on the fact in this reconstruction, it seems to have separated more by that time, and therefore
Yes, that's
passive
correct.
margins should be, okay, thanks.
There is a question from Eva Stukin. Could an unusually high rate of sediment subduction in the Mesoproterozoic have had implications for carbon transfer in the mantle and ocean atmosphere oxidation?
Well, I suppose it should, shouldn't it? I mean, this has been suggested by several individuals that if you're going to have enhanced subduction, you're probably going to have enhanced sediment subduction, and sediments carry carbon, right? Some sediments do.
Yeah. Any other questions, Kevin?
I'd like to make a structural observation, if I may. Some authors have attributed this A-type magmatism to lithospheric stretching. But because the Earth's surface is cold, the upper crust should fail in extension by normal faulting and fault block rotations like Basin Range province. But what you observe in these Mesoproterozoic provinces, such as the southeastern US, for example, where there are also extrusive equivalents of these anorogenic magmas, that seismic reflection profiling shows that these are regionally flat-lying. And similarly in Labrador, there are these 1450, 1500 million year intrusives bodies that are up to 100 kilometers in diameter and yet only a few kilometers thick. And yet they're regionally flat-lying. And so I don't think there's any evidence. In fact, I think there's contrary evidence to the idea that this magmatism is a consequence of lithospheric stretching. That means that if there's a thermal perturbation, it has to originate in the mantle, not in the lithosphere.
Yeah, thanks, Paul. That's an interesting observation. One thing I didn't mention is much of the A-type activity in the central US has rhyolites associated with it. In fact, there's a large volume of rhyolites in the basement. And one idea that has been suggested here is this might be a slip, a siliceous large igneous province that forms this area in the central US. That's at 1450 MA.
Can I just jump in? Do you know if those particular rhyolites have the sort of A2 or A1 type of composition?
The ones I see are A2. They're like the granites.
Which you would link as orogenic then?
That's how yes. But what I'm saying is I'm questioning that for that particular area. It may not be orogenic.
You know, those are certainly impressive. Both that at 1450, I guess, and also 1380. They're two separate major rhyolite provinces in the subsurface US there. Yeah. Yeah, those are impressive. And calling them, considering them as silicic large igneous provinces makes sense to me.
Kent, maybe you can say a few words, like how do you imagine subduction of thick accreted crust, like sort of how it would be transported to a mantle?
What can be transported? What kind of crust?
Accretionary origins on a margin of a supercontinent. How you overcome the buoyancy to transport them to the mantle?
Well, what I'm suggesting is subduction, erosion, and sediment subduction. Now, how far that sediment goes down is another question. Some data suggests that it's largely plastered, of course, underneath the continent in the lithosphere there. It doesn't go deep in the mantle at all. And other data suggest that some of it probably does go deep in the mantle. We have isotopic signatures in young hotspot volcanoes, which suggest that at least some continental crust somehow has been subducted deep into the source areas of some of these rich sources, these rich mantle sources that we see in some island basalts today. So some has to go down probably, but the volume that goes down may not be very large.
Well, oceanic crust gets subducted, and it's also positively buoyant, but its positive buoyancy is overwhelmed by the negative buoyancy of the lithospheric slab.
Yes.
Okay, any other questions for Kent or comments? Okay, Catherine Bifun wrote in the Grenville, the Mesoproterozoic plutons 1450, 1350 down to 1300 get younger towards the southeast as opposed to northwest.
So again, that's opposite of what my model would predict, is what he's saying, if I understand him right.
Yeah, sorry, it's the opposite of what your model would predict. So there are more Grenvillian experts in the audience. They might have more info than I do, but that's my sense that I think it's the anorthosites have quite variable age across the origin, but the A-type granites are younging toward the southeast generally.
That's interesting, because that would be an important constraint.
You steepen the slab.
Yeah,
Steepen the slab over time.
Yeah, they're actually all over the place in the eastern Grenville. If you include the mealy anorthosite massif and the mealy, the Nain complex. Nain complex goes, and plutons around that go from 1450 to 1.27. And those age mimicked ages all along the Grenville in the east, in the Pinoerian origin and central Grenville around Quebec, where you have A-type granites at 1.3, 1.4, 1.5. So it's a bit of a mix. I wouldn't say that there's a trend in either direction.
Yeah, and most of the anorthosites are not dated. The dates mostly come from the associated relatively minor granitoids, the manterites.
Yes, and in the examples where the anorthosites have been dated, they mimic the age of the granitoids around it in general.
Yeah, makes sense.
Okay, any other comments or questions?
Yeah, the Grenville is a globe encircling origin. How you explain that in stagnant lid escapes me.
Yes.
Mm-hmm.
But I really like your model of subduction erosion to explain for the absence or the lack of representative in the Mesoproterozoic. It makes a lot of sense.
Mm-hmm.
Well, it's sort of the default model. I couldn't think of anything else.
Mm-hmm.
If anybody else has got an idea out there that needs to be tested, it needs to come forward.
Well, the simplest explanation is always the best one.
The only danger with assuming lots of silicic material being eroded and subducted to mantle depths is that this material is buoyant at depths, and models are predicting a departure, kind of delaminate from the slab and then relaminate to the overriding plate. And then you should, as a minimum, have lots of magmatism related to melting of this deeply subducted crust.
So delamination may play a role there too. I didn't mention that, but that's right, Garth. I think your work has shown that delamination is another way to recycle it in subduction regimes.
Do you think it would equally apply to Paleoproterozoic time, time of 2.3, 2.4, when people talk about, again, slowdown of plate tectonics?
Yeah, that's a real problem. I'm working on that some more now because when I published my paper in 2009, everybody came on and showed me how widespread rocks were at the age of 2.3 to 2.4 in Canada and South America and elsewhere. Interestingly enough, we have zircon data now, detrital zircon data, approaching 1 million data points, which show a strong, an absolute strong minimum between 2.2 and 2.4 globally. So I think this is a global phenomenon. I'm not saying plate tectonics shut down, but something happened at 2.2 to 2.4 to account for an absolute global minimum in zircon ages.
But do you think the model that you presented for Mesoproterozoic could potentially apply to this time?
I don't know. I don't think we don't have as much data to support it.
Yeah.
Simply because in the 2.2 to 2.4, we don't have a lot of rocks preserved. So I think it's too early to say that it supports it.
It would be useful to have more than one episode of this reduced activity. So then, because then we will be dealing with at least 2 data points, because it's difficult to make robust conclusion about unique events.
Yes.
Okay, was one comment from Nick Roberts to everyone. Paul, I note that Bob Stern did not turn up. Well, I guess that doesn't require. Okay.
So Bob and I have talked a lot about this, and sometimes we're not on the same wavelength. If you're not on the same wavelength, it's hard to communicate.
Yeah.
Yeah, I know that Bob was planning. He even sent me a message that there will be a talk, but probably he had some urgent stuff to care about, because he was definitely planning to attend.
Anyway, one other thing I wanted to say, I see Brian Windley sitting there, and I didn't mention him. Brian reminded me this morning that in 1973, he and David Bridgewater were the first ones to show that these A-type granites formed in a belt from Laurentia to Baltica. And he sent me a copy of his 73 paper, which has this map in it. I should have mentioned that, I failed to do that.
Way to go, Brian. Brian helped get my career started.
I see he's disappeared now, but Brian, can you hear what I said? He's muted, so.
Okay, well, if no more comments or questions, maybe we stop here. And just one thing I want to announce, as we're thinking about continuing the seminar series in summer, we didn't decide yet if it would be weekly or bi-weekly. So far we're thinking about bi-weekly, but feel free to send to Alex and to myself any suggestions you have for speakers. We have a long list now, but we would like to keep it increasing, and especially for younger people in PhD or in postdoc, we are not aware about many of these names. So if you're advisor or involved in this study, feel free to nominate or self-nominate these people. And we sort of looking for a way to increase racial and gender diversity in this seminar. We're doing okay for gender, but I think we struggle to reach racial diversity. So please nominate people for us to invite. Okay, So with this, thanks a lot, Kent. We had a little bit of technical issues, but I think at the end it worked out well. And it was very good talk.
Thank you, Kent. Was a great time.
Yep.
Ken.